This is the first day of my life.
This lecture really has two parts. In the first part, we'll return to our discussion of the fundamental theorem of Galois theory and prove the last remaining piece, and also talk about some quick consequences of the statement of this theorem. And in the second part, we'll go back and address the one big thing that is missing from our proof of the fundamental theorem of Galois theory. And that is a proof of theorem 9 in section 14.1 of Dummett and Foote. Okay, so let's recall what the fundamental theorem of Galois theory says and what we've proven already. Let's say K over F is a Galois extension, and G is its Galois group. So G is Gal K over F. It's the group of automorphisms of K fixing F. There is a bijection between the set of subfields E of K containing F, so fields that fit into this diagram, and subgroups H of G. Here, I've written G at the bottom and the trivial subgroup at the top with H in the middle. Given by the correspondences, we take a field E to the subset of elements of G fixing E, and we take a subgroup H of G to KH, the fixed field of H. And these correspondences are inverse to each other. So in the last lecture, we proved several facts about this correspondence. We already know things like its inclusion reversing, and then we talked about the fact that K over E is always a Galois extension, and the conditions under which E over F is a Galois extension. So there's one remaining piece that we haven't talked about, and that's what I want to start this lecture with. So if E1 and E2 correspond to the subgroups H1 and H2, that is, E is the fixed field of H1, sorry, E1 is the fixed field of H1, E2 is the fixed field of H2, then the intersection of these two subfields corresponds to the subgroup generated by H1 and H2. So remember, what does that mean? There are several ways to think about it, but one is it's the smallest subgroup of G containing both H1 and H2. It's the intersection of all of the subgroups of G containing H1 and H2. Okay, so the intersection corresponds to the subgroup generated by H1 and H2. And the composite field, which remember is the smallest subfield of K containing both E1 and E2, corresponds to H1 intersect H2. As a consequence of this, we see that the lattice of subfields of K containing F is dual to the lattice of subgroups of G. So what does that mean? The lattice diagram for one is the same as the lattice diagram for the other turned upside down. And why does this first statement imply the second statement? Well, the key thing is to think about where the lines come from in these lattice diagrams. So you have a line in one of these lattice diagrams, let's say for subfields, between one subfield and another subfield, if one contains the other and there's no field in between them. So when you have the composite of two fields, you get a line. When you have the intersection of fields, you get lines. Same thing on this side. Subgroup generated by two groups give lines in the subgroup diagram, and the intersections give lines in this diagram. So I'll leave really writing down a formal proof as a good exercise for you to check here. So let's prove this statement. Really, we're going to prove part of it, and I'll leave the other part as an exercise. Let's prove this part about how the composite field corresponds to the intersection of subgroups. And we'll just prove this by first taking an element in the intersection and showing that it fixes the composite. Then we'll take an element that fixes the composite, and we'll show that it's in the intersection. So we're going to prove that the composite is the fixed field of the subgroup H1 intersect H2 by showing inclusion both ways. Okay, so let's take sigma in H1 intersect H2. Sigma's in H1. H1 is the set of elements of G that fix this subfield E1. So sigma fixes E1. And similarly, sigma fixes E2. And now let's think about where the elements of the composite come from. They are algebraic combinations of elements of E1 and E2. So why is that? Well, remember, in this Galois extension, we've only talked about what it means for a finite extension to be Galois. So you can think of this as being a finite extension. So it's generated by finitely many algebraic elements. So if you think of E1 as being, say, F adjoin alpha 1 through alpha n, and E2 being F adjoin beta 1 through beta m, you can think of the elements of E1, E2 composite as being polynomials in these alphas and betas with coefficients that are in F. So, okay, so that's what I mean by algebraic combinations of elements. So sigma fixes each one of those alphas and each one of those betas. So sigma fixes the composite field E1, E2. The converse, the other direction, is easier. If sigma fixes E1, E2, well, this composite field contains E1 and it also contains E2. I mean, by definition, it's the smallest subfield of K containing E1 and E2. So sigma fixes E1 and sigma fixes E2. So sigma's in H1 and sigma's in H2. So it's in the intersection. Okay, so that's the proof of this statement. And the proof for the statement about the intersection of two fields and the subgroup generated by H1 and H2 is similar. And I'll leave it for you as an exercise to write down a formal proof. So I really do recommend that you do this. I also recommend that you convince yourself that these two statements imply this statement about the lattice of subfields and the lattice of subgroups. But this one is easiest to understand really by looking at an example and thinking about where the lines come from. So I'll pause and erase, and I'll write down an example. I want to spend some time talking about examples of applications of the Galois correspondence. And let me start by saying there's a really great extended example at the end of section 14.2 in Dummett and Foote from pages 580 to 581. And that example is where K is a splitting field of x to the 8th minus 2 over Q, and F equals Q. So we have this extension that is Galois. You can show that this splitting field is the field generated by an 8th root of 2 and I over Q. And you can compute what the Galois group is by writing down all of the automorphisms of K fixing Q, or a generating set for them, and see that the Galois group here is this group that is not so familiar, but is closely related to some groups that we do know well. So this is called the quasi-dihedral group of order 16, but you can ask about taking subgroups and quotients of this group and seeing if you can find some of the interesting groups of order 8 that we know. So this is a great example to look at. This is a large group. It's sort of challenging to write down the lattice of subgroups and the lattice of subfields of K containing Q. But seeing them side by side is really helpful in understanding what the Galois correspondence is saying. So one other thing that I'll point out is, okay, it's clear that this field contains an 8th root of 2 and also a primitive 8th root of unity, contains all the 8th roots of unity. Because if you have the 8th root of 2 and you multiply by an 8th root of unity and you take the 8th power, then you still get 2. So here we're not seeing a zeta 8 here. So it's a good exercise to think about where that 8th root of unity is coming from in terms of these two generators. So that's another thing that you will see if you look at this example. Okay, so now I want to focus on some smaller examples that are easier to write down. We've talked quite a lot about this example of Q adjoin the cube root of 2 and zeta 3. This gives a Galois extension of Q. It's a splitting field for the polynomial x cubed minus 2 over Q. That Galois group we described in terms of these two automorphisms, sigma and tau. Sigma is this one that sent zeta 3 to zeta 3, and it sent cube root of 2 to zeta 3 times cube root of 2. And tau was this one that sent cube root of 2 to cube root of 2, and it sent zeta 3 to zeta 3 squared. And we saw that this group is isomorphic to S3. We can write down the lattice of subgroups of S3 in terms of these generators, sigma and tau. Here I've written the group on the bottom and the trivial group at the top. It has this one subgroup of order 3, index 2, and 3 subgroups of order 2, index 3. And then we can write down the fixed field for each of these subgroups. And by the Galois correspondence, we know that these are all of the subfields of this field containing Q. So you can check that you really do believe that I've done this correctly, especially with these 3 isomorphic cubic extensions of Q in the middle. Okay, so one of the consequences, one of the properties of the Galois correspondence that we talked about is this question of when, for an intermediate field E, is E over F a Galois extension? Well, this subgroup of order 3 inside this group of order 6 is normal. Right? A subgroup of index 2 is always normal. But the subgroup generated by tau, this subgroup of order 2 inside S3, is not normal. What does that correspond to over here? Q adjoins zeta 3 over Q is a Galois extension. But each one of these degree 3 extensions of Q, none of these are Galois. None of these subgroups are normal in this big group. So we know more than that. Not only do we know that this extension is Galois, but we know what its Galois group is. It's isomorphic to the quotient of the Galois group of K over F by the subgroup corresponding here. So the subgroup generated by sigma and tau mod the subgroup generated by sigma. Well, this is a group of order 6 mod some normal subgroup of index 2. This is isomorphic to Z mod 2Z. But we know more than that. We know more than what this Galois group is isomorphic to. We know where a generator comes from. So where does a non-trivial element of the Galois group of zeta 3 over Q come from? It comes from taking an element inside this group G that's in the non-trivial coset of this normal subgroup H, the one generated by sigma, in the big group. So we need to find some element that is in this big Galois group G that's not in this subgroup H. And we just take that element and we restrict it to this field. And that gives an automorphism of this field fixing Q. OK, so one sort of natural choice is to just pick tau and restrict that to Q adjoins zeta 3. And this is a generator for the Galois group of Q adjoins zeta 3 over Q. OK, so I'm going to pause and erase, and I'll talk about what happens when you take an element of the Galois group and you restrict it to a subfield that is not Galois over Q. So if you take a subfield corresponding to a subgroup that's not normal, what happens if we take an element here and we restrict it to this field? What we get is not an automorphism of this field fixing Q, but we do get something interesting. Let's continue with this example. If you take an element of the Galois group of Q adjoin cube root of 2 zeta 3 over Q, so something in this group generated by sigma and tau, and you restrict it to this subfield that is not Galois over Q, you don't generally get an automorphism of this field fixing Q. I mean, sometimes you do. For example, if you take the identity element and you restrict it to this field, certainly you get an automorphism, but you don't always get an automorphism. But in general, you don't get an automorphism, but you do get an isomorphism from this field to one of these conjugate subfields. So it's either an isomorphism with itself, an automorphism, or an isomorphism with Q adjoins zeta 3 times cube root of 2, or an isomorphism with Q adjoins zeta 3 squared and the cube root of 2. And OK, you take an element in here, you restrict to this subfield. How do you know which one you get? Well, this subfield corresponds to this not normal subgroup generated by tau inside the big group. You get an isomorphism to one of these 3 conjugate subfields. which one you get depends on which coset of the subgroup generated by tau, the subgroup corresponding to this field under the Galois correspondence, this element is in. So you take an element in here, you restrict it to this field, you get an isomorphism to one of these three conjugate subfields. Which one of those three? It depends on which coset of this subgroup generated by tau in the big group the element you're restricting is in. Okay, why is that true? Because in our discussion of the properties of the Galois correspondence, we talked about this correspondence between embeddings of E fixing F and cosets of H inside of G.